Any questions about anything from last time? Last time I introduced at the end some words that we're going to start thinking carefully about. I like this set here. The purple set is the set of rational numbers p so that p squared is less than 2. And now we know that the square root of 2 is an irrational number. So I could put it less than or equal to there, and it would be the same set, because there is no rational number whose square is 2. That's why this is my favorite picture to put here. And so the concepts we're going to talk about today are upper bounds and lower bounds, and in particular, extreme ones. This m here is an upper bound because it's bigger than or equal to everything in S. So it's an upper bound for S. And what that means is that S is less than or equal to m for all S in S. And if I try to slide that m down until I can't slide it any further, keeping it at an upper bound, I hit square root of 2 and I can't go any further. Square root of 2 is the least upper bound. And we'll write square root of 2 equals least upper bound, LUB of est. I'm going to replace LUB with sup pretty soon for supremum, but I don't want to get carried away with words at the moment. And of course, the similar concept, this is little m here, is a lower bound. And that means that S is greater than or equal to little m for all S in capital S. And then I could slide that little m until it hits and can't go any further. And when it hits minus the square root of 2, this turns out to be the greatest lower bound. I can't slide it any farther. The greatest lower bound. And we write minus the square root of 2 equals the GLB of S. Questions about those words? Not every set has to have an upper bound or a lower bound. For example, all of Q doesn't have an upper bound or a lower bound. And Q less than or equal to 0 wouldn't have a lower bound, but of course 0 would be an upper bound, etc. So I think that's the definition of upper bound, lower bound, etc. So I'm not going to write that out. But there's some other bounds I should mention. So here's some words. S, bounded from above, just means there exists an upper bound. So I'll use exists an upper bound M. And of course, bounded from below, there exists a lower bound. little m. And you sometimes will say that a set is bounded, and that just means it has both of those things. This is called bounded. When it has both an upper and a lower bound. Upper and a lower. Now we'll start using abbreviations. BND for bound. Yeah, so the examples I was mentioning there. Q, the whole thing, is unbounded. Let's say if I take Q plus, namely the positive rational numbers, then of course it's bounded from below, but not from above. So it's bounded below, but not above. And the Q negative numbers, negative rational numbers, is bounded above, but not below. Okay, so a huge fact today. Is that if the set's bounded above, then it has a least upper bound. That turns out to be kind of a deep, important thing. It's very believable from my picture because you sort of slide that thing until you can't slide it anymore. And then you hit the least upper bound. So the huge fact is if a set S, subset of the real numbers, is bounded above, so that means there exists an upper bound, then there exists a least upper bound. So it's an existence statement. There exists a least upper bound. There'd be a similar statement for the greatest lower bound. If a set's bounded from below, then of course there's a greatest lower bound. Same thing. You can always flip them around upside down and see one from the other, just by taking minus the set in place of the set. So I won't write that down, but it's equivalent to this thing. So it's a huge philosophical fact. And in fact, calculus is 100% dependent on this fact. So sometimes that's called the least upper bound principle. This is sometimes called the least upper bound principle. The book calls it completeness property of the real numbers. Because it's equivalent to the completeness property. I'll say a couple more remarks about that later. A fascinating thing is that it doesn't follow from the axioms that we've been writing down. It's kind of an axiom itself. So, interesting fact. It doesn't follow. Excuse me. from the field axioms. That's the stuff about multiplication, addition, distributive law, etc. The field axioms plus the order axioms. So you can actually think of it as an axiom. So we need it as an axiom. And that bugged Dedekind. Need it as an axiom. Okay, so a wonderful thing that Dedekind did is he showed, if you understand the real numbers in a certain way, you can show that it's a consequence of the definition of the real numbers. So it's hard to talk mathematically about the line I draw on the board. It's a thing. You feel it's a thing. We understand, there's rational stuff all over the place, and things like the square root of 2, you poke your finger there, and you say, aha, that's the square root of 2. I see it, I feel it. But, asking yourself, what the heck is it from a mathematical point of view, is a task. And Dirichlet started that task by deciding what the integers, the positive integers were. And he came up with a model for the positive integers. And he could prove all the basic facts about integers. And then, of course, he could prove all the basic facts about rational numbers. And he came up to thinking about what the heck is a real number. And he came up with this brilliant idea. I mentioned it in previous lectures. So let's see. He called these things. He didn't use his own name. They're called cuts, Schnitz in German. So he would partition the rational numbers. And I would draw this little thing right here because I'll make different colors here. I'll make the p's be less than, these p's to the left are all less than these q's to the right. So we partition the rational numbers into two sides. And everything in the left side is less than everything else on the right side. That's called a Schnitt. And we saw the square root of 2 makes a Schnitt. All the q's that are bigger, so their square is bigger than 2, and all the p's so that they're less than 2. That partitions the rational numbers into a big side and a small side. Okay? There are rational numbers, and these are rational numbers. And all the p's are less than all the q's. All right? And you think that this is corresponds to a real number. And you think that this is equal to r right here. And if r is a rational number, then you make the r be in the purple side. So okay, so that's what Dedekind was thinking. And then the fascinating thing is that this particular axiom is just an obvious fact. So how did Dedekind show the least upper bound property? The least upper bound property let's see. So the least upper bound property is the least upper bound property of S. Take the union of the left-hand side of those Schnitts. So you take the union of the left-hand side of all the R, left-hand sides of the cuts, with the R's in S, and that's the left-hand side cut of the least upper bound. Well, let's see, I'm sorry, so this is the union of the left-hand sides of the cuts, and this is the left-hand side of the cut for the LUB. Very clever and very insightful. So what he showed is that this basic fact follows if you understand the real numbers to be what he understood them to be. So what Dedekind did is he came up with a model called notches on our stick. Our model is a model for the positive integers. And so was Dedekind's curly bracket tower of sets thing. He came up with a model for R where the LUB property is demonstrable. Holds from definitions. Okay. So it's important when you're talking about math that you're talking about something. And this is a way to talk about real numbers like they're something. Yeah.
So for the LUV property definition here, do you need a right side of the cut?
Well, the right side would be the complement of the left side.
Okay.
Yeah, so there would be a right-hand side, but first you mess around with the left-hand side. You just take the union, you pile them all up, stick them together, and then the right-hand side would be, everything would be bigger than that. I mean, there's some work in doing it, but that's exactly how he did it. And that's a very easy thing to do. The hard thing to do was proving all the other axioms. So it's lots of work. So that the rest was lots of work. As for example, he would have to define addition, for example. So we'd have cuts, an R1 and an R2. R1 plus R2 would correspond to, the left-hand side would be, okay, there'd be this place. Left-hand side would be all the P1s plus P2s. And the right, first you have to show that you take a P1 plus P2 and you take a Q1 plus Q2. You have to show that those Q1 plus Q2s are bigger than all the P1 plus P2s, and you partition the rational numbers into two things. And it's kind of tedious and a lot of work, and multiplication is even harder because the signs, if you have two negative things and you multiply them together. So Dedekind was good at hammering down the little details, and he did it. So it's work. And he showed that all the axioms hold, and so he had a model for the real numbers. Okay, so in this next section, you got to get comfortable using these facts. And here's one that's a good illustrative thing that we're going to be using later. Fact. M is equal to the least upper bound of S if and only, it's kind of like a epsilon delta version of what it means to be a least upper bound. For every epsilon bigger than 0, there is an S the book likes to do, I'm not going to do it, but the book likes to do, okay, there is an S in S such that S, let's see, it's the least upper bound, and so for every epsilon, there's an S in S such that S is bigger than M minus epsilon. Okay, the book, like when it says things like this, it writes there's an S sub epsilon. That little S sub epsilon means that the S depends on epsilon. You give me an epsilon, I'll find you an S. And so to emphasize that it depends on epsilon, the book likes to put an S sub epsilon there. It's a good idea. Maybe I should, but I might slip up and not do that. So I'm not going to endanger myself. Okay, let's, whenever you're thinking about these things, I'm going to demonstrate this. And this is kind of what you have to get used to. It's how to demonstrate these things from the definitions. Okay? And this is an important one. When I'm going to demonstrate these things, it helps me a lot to draw a picture. So here's why. Okay, here's the real numbers. Here's my M. And my set is over here. And I'm thinking of M as a least upper bound. M is an upper bound. Oh, let's see, I skipped something. Fact. Suppose, I should have supposed here, in addition to what I have, suppose M is an upper bound for S. Okay. Then M is the least upper bound if and only if that. Okay. So there's the picture. M is right there. And so M minus epsilon is going to be over here somewhere. And so when I draw that picture, you believe, of course, there's going to be an S stuck between M minus epsilon and epsilon. Okay. But I have to, let's see, when there's an if and only if thing, that means there's two directions to check out. So let's think about this direction. So to demonstrate this direction, I have this upper bound, and I suppose, so we suppose the upper bound, M, is the LUB. Okay. Well, let epsilon be bigger than 0. I have to show that there's an S that satisfies that property. So, how am I going to do that? Ideas? Using the words. Well, my picture there makes it obvious to me that M minus epsilon is less than M. M minus epsilon is less than M. M is the least upper bound. So what does that mean? M is the least upper bound. M minus epsilon is not an upper bound. m minus epsilon is not an upper bound. Well, if you're not an upper bound, that means it's not the case that you're bigger than or equal to s for all s. So it's not true that s is less than or equal to m minus epsilon for all s. That means there exists one that's bigger than that. With s bigger than that. So check. We just showed that if the m is a least upper bound, then it has this property that give me any epsilon, I can find you an s. Okay, and it just follows from the meaning of the words. It's kind of a tongue twister because there's so many knots in there. If you write it out carefully and think about it and draw the picture, it should be within reach. Let's see, that's one direction. Any questions about that half? Let's think about the other half. Going this way. It's maybe the weird one. I have to show that I'm assuming this property, this sentence about for any epsilon there's an s thing. Okay. So m is an upper bound. And the epsilon stuff is true. For m. Okay. Well, let's see. I'm going to go back. I'm looking at my picture again. There's an m. There's an m minus epsilon. And there's always an s stuck right here. Let's see. I don't have an m minus epsilon yet. Let's suppose that if x is less than m, okay, that's going to be my x right there. I'm going to let epsilon be equal to m minus x. That's, of course, bigger than 0. And then this x would be equal to m minus epsilon. And so then I would get an s. We get an s with x less than s less than m. This little thing right here shows that x is not an upper bound for s. So the aha moment is, because of this, x is not an upper bound. Okay. M is, and anything less than m isn't. That means that m is the least upper bound. So what I've shown you here is, m is an upper bound. Anything less isn't. So m is the least upper bound. Okay, so this kind of math is just understanding English and the meaning of the words. It's remarkable how much the GRE verbal score predicts success in math, because writing about math and thinking about math has a lot to do with understanding sentences and how to put them together. Anyway, it takes some effort to get used to this line of reasoning. And when you did geometry in junior high, it was kind of a fun game to play. This is taking that into the realm of real numbers. Questions about anything? Yeah. Sorry, here.
Yeah. So the m is upper bound and anything less than it isn't. So we can determine m is the least upper bound. But why is that?
Oh, we assumed that it was an upper bound.
We will assume that, and how we get is the least upper bound.
Because if you take any number less than m, it's not an upper bound. So if you look at all the upper bounds, there's nothing to the left of m. So m is the least. That's what it means to be the least. There's nothing smaller. Yeah. Kind of a silly example to think about. S could be a singleton, say pi. That's kind of a dumb thing to think about, but then these things can become sort of, they still are true, but they're silly to think about. Statements seem silly but are true. Oh yes, I need to mention those words I was going to talk about. The fancy word, we had fancy words. And mathematicians like the fancy words more than lub and gulb. The fancy words are the least upper bound is equal to the supremum. It's Greek. The supremum, and we write soup, say soup. And the greatest lower bound is equal to the infimum. Infimum. And we write inf instead. So remember we had injective, bijective, and surjective. Those are fancy words for one-to-one, onto, etc. And these are fancy words for LUB and GLB. And we'll use those symbols. Once you get used to meaning, then of course soup and inf is easier to say than LUB and GLB. Okay, I need to make a remark about the word completeness. In freshman calculus, somebody probably told you R complete means that every Cauchy sequence has a limit. Of course, we haven't even talked about sequences yet. The LUB property is continuous, is equivalent to that. statement. And so let me just draw you a picture here of how you would feel, the way you feel about this fact. This isn't a proof or anything, but we had the square root of 2, and we had rational numbers to the left and rational numbers to the right. You could take a Q1 over here somewhere, and then take a rational number over here, Q2, and then you could start squeezing in Q3, Q4, Q5. The Q's are getting closer and closer together. And you can believe from that picture that they're going to converge on the square root of 2. So a Cauchy sequence means the Q's are getting closer and closer together. The Q sub n's are getting closer and closer together. Completeness means they have to get close to a limit. And in fact, you can mess around. It's actually more technical than this. I made these nice and alternating between being bigger and smaller. So you'd believe, of course, I could take the supremum of the ones on the left, and I could take the nth of the ones on the right, and show that those must be the same, and therefore that's going to be the limit. That's how I would use today's material to show that this sequence has a limit. Sup for the left-hand side ones and the nth for the right-hand side ones. The fact that they're getting close together means that those two numbers would have to be the same, and they'd be the square root of 2. Completeness means the Q's must converge to a limit. That's a very important fact from calculus, and it follows from the least upper bound property with some work. We're going to do that work later. Let's see. Funny, Archimedes started thinking about these things way back, and he did, I would say, invent calculus. He came up with ways to calculate areas that were very much like Riemann sums and integrals, and took limits and did brilliant things like that. And he grappled with this idea of, similar to the least upper bound property, but Archimedes called this the Archimedean property. And it's highly related to the least upper bound property. And it helped him invent calculus. If R is a real number, then there's a positive integer bigger. There is an n, it's a natural number, with n bigger than or equal to r. It's also related to the property that there's no smallest positive real number. That's what was bugging Archimedes. So he was thinking about stuff like that. Seems like a no-brainer, but bugging Archimedes even back then. And so this is related to our least upper bound properties. Some books start with this and go to the least upper bound property. Some books start with least upper bound property and go to this. But you need Dedekind's, you need somebody like Dedekind to tell you what a real number is so that these things are true. Anyway, a fun fact is that this follows from the least upper bound property. Let's think about why that's true. Why? Oh, let's see. Suppose the Archimedean property didn't hold. Let's give ourselves an R. And suppose the Archimedean property failed. Failed for R. Well, then that would mean there's no n that's bigger than or equal to R, which means that all the n's are less than R. So there is no n with n bigger than or equal to R. So all the n's are less than R. So n is less than R for all n. That means R is an upper bound for the natural numbers. And so there, now we know from the least upper bound principle that there's a least upper bound. Least upper bound, or soup of the natural numbers. Well, what should I, how can I see it's a least upper bound for n? Should I do next? Using the words to figure out that this is going to lead to a contradiction. Any ideas?
Does this mean there is a greatest natural number?
Ah, getting to, yes, it does. You can think of it that way. But you have to use the word somehow. One of those things we did, you remember my picture, my picture from earlier. I had a least upper bound. And I would have an m minus epsilon here. And epsilon could be anything small. Well, what would be the reasonable thing to do here? What should I take my epsilon to be? My epsilon, I don't know, I got to take epsilon to be something. And I'm going to get, that's going to give me a set in my S, which is n. So I'll get an m in my set, which today is n. This is going to be m minus something. It's like I could take, I shouldn't take n to be I shouldn't take epsilon to be 1,000. I maybe could take it to be a half. That would be fun. A half would be really good. I'm going to take it to be equal to 1. And the thing I was messing around with today, earlier in the hour, said, well, by the definition of the least upper bound, I can find a thing in the set that's right there. And now n plus 1 would be an m. I'll make, red doesn't really show up here, but n plus 1 is bigger than m. Ouch. That means that m is not an upper bound. Even though we assumed it was, even though the principle says it exists. And that contradiction means there is no such R. Questions about that? Kind of silly. So this is also related to the fact we can do things like it's related to no smallest positive real number. And that's what Archimedes was messing around with. You know, the fascinating thing is, you know, Dedekind was reacting to history of calculus. Newton was trying to do calculus, and he invented wacky, weird things like fluxions and infinitesimals, and tried to make sense out of those. And of course, Dedekind was a stickler for details, and those things didn't make sense to him. He wanted to believe in calculus, and his mission was to make it rigorous, so that, kind of like classical geometry that the Greeks did, axiomatic, whereas Newton was being pretty loose with talking about infinitesimals and fluxions and things like that. Funny thing, there's something called hyperreal numbers, where people, I think it was Donald Knuth, axiomatized Newton's concept of fluxions and infinitesimals, and he was able to make it axiomatic in a fascinating way. But it's different than Dedekind's thing. Dedekind's thing corresponds more with reality and what you believe the real numbers to be. And when you point your finger at the square root of 2 on a line, you feel like it's, you know, filling in the rational numbers. That's a really strong feeling, and it makes a lot of sense. Whereas fluxions was pretty wild and crazy. But you can make a theory out of it that's very equivalent to the standard theory. In fact, what's Knuth obtained is called a non-standard model of the real numbers. It's fascinating mathematical logic. Okay, that feels like enough for today.
So here, if the is n plus 1 is greater than m,